In the 19th century, physicists faced a question that seemed almost embarrassing in its simplicity. Light traveled from the sun to the earth across 93 million miles of apparent emptiness. But waves, everyone knew, needed something to wave in. Sound required air. Ocean swells required water. Ripples required a pond. What, then, carried light across the void of space? The answer, agreed upon by nearly every serious scientist of the era, was the luminiferous ether. This ether was no ordinary substance. It had to be everywhere, filling all of space, permeating the room you are sitting in, passing through your body and through solid stone. It had to be perfectly transparent, offering no friction to the planets that swept through it for billions of years. Yet it also had to be astonishingly rigid, more rigid than steel, because light waves oscillated with extraordinary speed. A jelly that was simultaneously stiffer than diamond and thinner than nothing. James Clerk Maxwell, whose equations of 1865 unified electricity, magnetism, and light itself, took the ether seriously. So did Lord Kelvin, so did Hermann von Helmholtz. The greatest minds of the century built their physics on an invisible sea nobody had ever touched, weighed, or seen. It was the stage upon which all of nature performed. And yet, a troubling implication hid inside the elegance. If the ether filled all of space and stood still, then the Earth must be moving through it. Our planet orbits the sun at roughly 30 kilometers every second, a relentless journey around a vast ellipse. Racing through a stationary ocean of ether, the Earth should feel a current, a headwind of invisible substance streaming past. Sailors know that a ship moving through still water creates the sensation of a breeze. Why should the Earth be any different? If that ether wind existed, it would leave a fingerprint on the speed of light itself. Beams traveling with the wind should move faster than beams traveling against it. The difference would be minuscule, almost impossibly small. But if someone could measure it, they would prove that the invisible ocean was real. That challenge would consume a young naval officer from Cleveland. Albert Abraham Michelson was born in 1852 in a Prussian town that is now part of Poland and carried to America as a child. His family settled amid the mining camps of the California and Nevada frontier, where his father ran a dry goods store. There was nothing in that dusty beginning to suggest a future obsession with the fastest thing in the universe. But Michelson found his path through discipline. In 1869, he entered the United States Naval Academy at Annapolis, appointed after a personal appeal reached President Ulysses S. Grant. He graduated in 1873, and it was while teaching physics to midshipmen that he became captivated by a single problem: measuring the speed of light with a precision no one had achieved. In 1879, using rotating mirrors along a stretch of the Severn River, the 26-year-old officer measured light's velocity at 299,940 kilometers per second, a figure remarkably close to the modern value. He was becoming, quite literally, the most exacting measurer of light alive. Michelson was not content with any ordinary accuracy. He wanted to detect differences finer than a fraction of a wavelength, distances of millionths of a centimeter. To chase the ether, he would need such precision. In 1885, he joined forces with Edward Williams Morley, a chemist at Western Reserve University in Cleveland, Ohio. Morley was a bearded, meticulous experimentalist, famous for measuring the atomic weight of oxygen to extraordinary decimal places. He had the patience of a saint and the hands of a surgeon. Together they made a formidable pair. Michelson, the driven visionary, Morley, the careful craftsman. Both understood that a single misalignment, a trace of vibration, a whisper of temperature change, could ruin everything. Cleveland in the 1880s was a booming industrial city of iron and railroads, an unlikely stage for one of history's most consequential experiments. In the basement of a campus building, the two men prepared to build an instrument sensitive enough to feel the invisible wind of the cosmos. First, they had to understand precisely what that wind should look like, and exactly how fast the Earth was supposed to be plowing through the ether. Imagine standing on a train, moving at speed, sticking your hand out the window, Even on a windless day, you feel a rush of air against your palm. That rush is not weather. It is your own motion made tangible. This was the logic of the ether wind. If the ether filled space and sat still, then the Earth, orbiting the Sun at 30 kilometers per second, must be plowing through it. From our perspective, the ether would seem to stream past us, a steady, invisible current flowing in the opposite direction of our travel. Now consider light moving through that current. A beam fired in the same direction as the Earth's motion would, according to the theory, be swept along by the streaming ether. A beam fired against the motion would fight upstream, slowed by the oncoming flow. And a beam fired sideways, across the current, would drift like a swimmer crossing a river, forced to angle slightly to reach the far bank. The differences would be extraordinarily tiny. Light travels at nearly 300,000 kilometers per second. The Earth's 30 kilometers per second is only 1/10,000th of that. The effect on the measured speed would be proportional to the square of that ratio, a number of about 1 part in 100 million. To grasp how small that is, imagine trying to detect a single second lost across more than 3 years. No clock, no timer, no direct measurement could catch it. And yet the physics was clear. If the ether existed and the Earth moved through it, light must travel at slightly different speeds in different directions. The prediction was precise, quantitative, and testable in principle. The only obstacle was the almost inconceivable precision required. To capture a difference of 1 part in 100 million, you could not simply race 2 light beams and compare stopwatches. You needed a way to make light itself reveal the discrepancy, to turn an invisible fraction into something a human eye could read. The answer lay in the wave nature of light, and in a machine unlike anything built before. Michelson and Morley were about to attempt the impossible. The instrument was called an interferometer, and its principle was breathtakingly clever. A single beam of light would strike a half-silvered mirror set at 45 degrees. There the beam would split in two. One half would travel straight ahead to a distant mirror and bounce back. The other half would travel at a right angle to a second mirror and return. The two beams, reunited, would overlap. Because light is a wave, the crests and troughs of the two returning beams would either reinforce each other or cancel out, producing a pattern of bright and dark bands called interference fringes. Here was the trick. If one beam took even slightly longer to make its round trip, slowed by the ether wind, its waves would arrive out of step. The fringes would shift, and the human eye, aided by a telescope, could detect a shift of a mere 100th of a fringe. This was sensitivity beyond any stopwatch, precision measured in fractions of a wavelength, distances smaller than a 5,000th of a millimeter. But such sensitivity was also a curse. The slightest tremor would blur the pattern. A footstep on the far side of the building, the rumble of Cleveland's traffic, a passing horse cart, even a change of temperature warping the metal, could destroy the reading. So in 1887, Michelson and Morley built something monumental. They mounted the entire apparatus on a massive sandstone slab, about 1.5 meters square and a foot thick, weighing hundreds of pounds. This slab floated in a circular trough of liquid mercury, letting the whole assembly rotate smoothly and silently, isolated from the shaking earth. To lengthen the light's path and multiply the effect, they bounced the beams back and forth between mirrors until each traveled some 11 meters. They set it in the basement to steady the temperature. Every element was engineered to eliminate error, to strip away every excuse, until only the ether itself remained to be measured. When they were finished, they possessed the most sensitive optical instrument ever constructed. Now, in the summer of 1887, they would set it spinning and watch for the fingerprint of the invisible sea. In July of 1887, in the basement of a dormitory at Western Reserve University, the experiment began in earnest. The routine demanded almost inhuman patience. To avoid disturbing the delicate mercury float, one of the men would set the great sandstone slab turning with a gentle push, and then walk slowly around it, circling with the apparatus as it rotated. Bending to the eyepiece of the telescope, he would read the position of the interference fringes at 16 marked points during each full revolution. The theory made a definite prediction. As the apparatus turned, one arm of the interferometer would swing into alignment with the Earth's motion through the ether, while the other arm turned crosswise to it. At those orientations, the ether wind should slow one beam relative to the other, and the fringes should visibly drift, shift, and then drift back as the machine continued to spin. Michelson and Morley expected a fringe shift of about 4/10 of a fringe, and their instrument could detect a shift 20 times smaller than that. There was, they believed, no way to miss it. They took their readings at different times of day, catching the Earth's rotation carrying the apparatus into new orientations. They took them across several days in that summer because the Earth's orbital motion around the Sun would shift the direction of the ether wind over weeks. They observed at noon and in the evening, methodically, patiently, recording columns of numbers in careful hands. Every possible objection had been anticipated. The slab floated free of vibration, the temperature held steady, the light path was long, the rotation was smooth, the reading precision was extraordinary. If the ether existed, if the Earth truly moved through an invisible ocean, this machine would feel the current. It could not fail to feel it. Around the world, physicists waited. Maxwell himself, before his death, had doubted such a measurement could ever be made, calling the effect too small to catch. Michelson and Morley had proven the effect catchable. Now the fringes stood ready to reveal the motion of the Earth through the fabric of space. The two men bent to their telescope, spun the great stone, and looked. What they saw would unsettle physics for a generation. In July of 1887, Michelson and Morley gathered their data. The procedure was patient, almost meditative. At noon and again in the evening, they set the sandstone slab drifting on its bed of mercury and turned it slowly, one full rotation, every 6 minutes. Through the small telescope, an observer walked beside the moving stone, calling out the position of the interference fringes at 16 marked points around the circle. If the ether existed, those fringes should have crept sideways as the arms swung into and out of the ether wind. Their instrument was sensitive enough to catch a shift of 1/100th of a fringe. They expected roughly 4/10. The theory predicted a clear, unmistakable dance of light. What they saw instead was almost nothing. The fringes trembled, but only from the vibration of the building, the footsteps in the street, the faint warmth of the observer's own body. When they averaged the readings, the genuine displacement fell below 1/40th of a fringe. So small, it vanished into the noise. There was no ether wind. There was no signal at all. For two men who had built the most precise optical instrument on Earth, this was not triumph. It was bewilderment. Michelson had spent years chasing the ether, and now his masterpiece returned a blank. In his report, he called the result of the anticipated effect probably less than 1/6 of what theory demanded, and confessed the outcome was so decidedly negative that the ether hypothesis seemed doubtful. He considered the entire experiment a failure. Morley agreed the finding was inconclusive, a problem to be solved rather than a discovery to celebrate. They even planned to repeat the measurement across a full year, hoping the seasons might reveal what the summer had hidden. The two colleagues did not grasp, in that Cleveland basement, that they had just measured one of the most important quantities in the history of science: zero. The absence they recorded would not stay quiet. It landed among the physicists of Europe like a stone in still water, and the men who had built their careers on the invisible ocean of ether now faced an unbearable question: how to save a medium that refused to be found. The null result did not destroy the ether overnight. Instead, it triggered a decade of ingenious rescue attempts, as Europe's finest theorists tried to explain how a very real ether could hide so perfectly. The boldest answer came in 1889 from an Irish physicist, George Francis Fitzgerald, writing a short letter to the American journal Science. His idea sounded like desperation, dressed as insight. What if, he proposed, motion through the ether physically squeezed objects along the direction they traveled? An arm of the interferometer pointing into the ether wind would shrink by exactly the amount needed to cancel the expected fringe shift. The stone, the brass, the very light path itself all compressed just enough to erase the signal. Independently, the Dutch physicist Hendrik Lorentz reached the same conclusion and gave it mathematical rigor. By the 1890s, he had derived a precise contraction factor tied to the ratio of an object's velocity to the speed of light. At Earth's orbital pace of 30 kilometers per second, the shrinkage amounted to a few parts in 100 million, utterly invisible, yet enough to swallow the experiment's expectation whole. Lorentz went further, introducing a strange new quantity he called local time, a mathematical bookkeeping device that different observers would use depending on their motion. The equations worked, they matched the data, and yet something felt hollow. The contraction had been invented for one purpose: to protect the ether from a fact that contradicted it. It explained why the ether could never be detected, which raised an uncomfortable question. What good is an invisible ocean that leaves no trace, exerts no drag, and shrinks the very rulers you would use to find it? Physicists had built an elaborate scaffolding of hypotheses around a medium no one could measure. The theory was bending under the weight of a single stubborn result, and the joints were beginning to crack. Lorentz himself sensed the strain. His transformations described nature beautifully, but their meaning remained murky. What was needed was not another patch, but someone willing to ask whether the ether had ever been necessary at all. That someone was working, unnoticed, in a Swiss patent office. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper with a modest title, On the Electrodynamics of Moving Bodies. Albert Einstein held a third-class position at the Federal Patent Office, examining applications for electrical devices. He had no laboratory, no famous mentor, no telescope of his own. What he had was a willingness to abandon an assumption that everyone else had clung to. Einstein began not with the ether, but with two simple postulates. First, the laws of physics are identical for all observers moving at constant velocity. Second, and this was the audacious leap, the speed of light in empty space is always the same, roughly 300,000 kilometers per second, no matter how fast you move toward or away from its source. From these two ideas, everything followed. There was no need for an ether wind, because there was no ether to blow. The Michelson-Morley experiment found nothing, because there was nothing to find. Light did not travel through a medium, it simply moved at its constant speed for everyone. To make the postulates consistent, Einstein rederived the very equations Lorentz had used, but he gave them a radically new meaning. Length contraction and time dilation were not mechanical effects of pushing through an invisible fluid. They were properties of space and time themselves. Moving clocks truly ran slow. Moving rulers truly shortened. Simultaneity itself dissolved. Two events that looked simultaneous to one observer occurred at different moments for another. Historians still debate how directly the Cleveland experiment shaped his thinking. Einstein rarely credited it prominently, sometimes claiming he was barely aware of the specific result when he wrote his paper, focusing instead on the puzzles of electromagnetism and moving magnets. Yet the null result had saturated the physics of his era. It was the fact everyone was trying to explain away, and Einstein's genius was to stop explaining it away, to treat the absence of an ether wind not as a mystery to be patched, but as a fundamental truth about the universe. The luminiferous ether, the invisible ocean that had filled all of space for a century, was gone, and with it went comfortable, absolute notions of space and time that had stood since Newton. Consider what Michelson and Morley believed they had done. They had built the most sensitive optical instrument on Earth, floated it on Mercury, and turned it patiently beneath a Cleveland basement, all to catch a wind of ether that never came. They walked away disappointed. Michelson would call the experiment a failure for the rest of his life, even as he became, in 1907, the first American to win the Nobel Prize in the sciences. He had wanted to measure the ether's flow. Instead, he had helped prove the ether did not exist. That is the strange arithmetic of this story. An experiment designed to detect something found nothing, and that nothing rearranged the foundations of physics more violently than any positive discovery of its age. The fringe shift they failed to see, smaller than 1/40th of a wavelength, quietly demolished a belief that had stood since the days of Descartes and Newton. That empty space was filled, that light needed a medium, that motion had an absolute frame of reference. From the wreckage rose relativity. Time slowed for the fast-moving. Distances shortened. Mass and energy became two faces of a single quantity, bound in the equation E equals mc squared. The rigid stage of Newtonian space and time gave way to a flexible fabric that bends, stretches, and folds. Later, this same fabric would predict black holes, the expanding universe, and the ripples of gravitational waves detected more than a century later, themselves measured by interferometers descended directly from Michelson's design. The instrument that found nothing became the instrument that would eventually hear the collision of stars. There is a lesson buried in that mercury-floated stone. Science advances not only through triumphant discovery, but through honest confrontation with the unexpected. Two careful men reported a result they did not want, could not explain, and considered a defeat. They resisted the temptation to fudge, to hope, to look away. And because they told the truth about their empty measurement, they handed the next generation the key to a deeper universe. Their failure was the most productive in the history of science. It reminds us of something physics learned the hard way in a Cleveland basement in 1887. Sometimes finding nothing changes everything.